So, good morning, everyone. Let's wait a little while longer because people are still joining, and then we get started. I'll already switch to my presentation. Okay, that's a little bit better. Okay, I think we can get started. All right, so welcome to this training session on containers for HPC. So this is the QR code that leads you to this webpage, and that webpage is just a brief overview of what we're going to talk about, and it also contains, which is more interesting, a link to the repository on GitHub, which is this one, and that contains quite a lot of things. Among them, the presentation I'm going to use, so you have access to that without any issues. There is also, and that's even more interesting, a directory with examples, some of which I'll talk about, some of which I'll touch upon. Some solve some pretty exotic cases, but nevertheless, it can be useful to have a look at it. I'm also putting the link in the chat because the QR code is a little bit annoying. That's mainly intended for on-site trainings. All right. So, of course, feel free to follow us being the Flemish Supercomputing Center on LinkedIn. That gives you the latest news, well, our latest news on HPC, our infrastructure, our services, but sometimes also more in general, and it can be interesting to follow us. Okay, so about the training in general, trainings in general in my case. So this is an online training that makes it a little more awkward in the sense that, yeah, you can't see participants, and that is always a little talking into a black hole. So what I like about trainings is that they are as interactive as possible. So for an online training, please use the chat. We're also not that many. So if you have questions, also feel free to just activate your microphone. If you're more comfortable with the chat, feel free to do so. During the presentation, I'll keep an eye on the chat at all times, and I'll answer your questions. Maybe not straight away, because I think, okay, this is something that I would prefer to postpone till a later moment when it's more appropriate. I recognize some faces, well, okay, some names. Hi, Elisa. Not that long ago, usually 2 days ago. Okay, so I'm going to put the link in the chat again because I think some people joined a little later, and then they don't see the chat history. All right, so let's get started. So there are a number of ways to run containers on systems. I'm not going to say HPC systems. It also holds for HPC systems, but on HPC systems we have some limitations which I'll talk about. So there are a number of ways. So one of the ways to do that is using Singularity. and that was originally developed at the university, at Berkeley Lab, well, research facility at Berkeley Lab, and they turned that into a startup, which is called Scilabs, and which is still quite active. So they have a product which is called Singularity, and that is still available. So it was originally intended as an alternative to Docker, mainly to Docker, because, well, you would have to be basically from a almost from a different planet not to have heard from Docker about Docker in the past decade. So Docker is a very popular technology in IT, which allows you to run containers on many systems. And why is it popular? Basically, it is a very nice way to deploy services, like for instance databases, like for instance web services, and so on. Why? Because basically it puts a layer of abstraction between your application and the hardware it's running on. And that is, of course, a rather nice thing, because that means that if I can define my container, install the applications in my container, I don't really care which hardware and even which operating system is used on the system where I deploy and run my container. So that's something that is very neat. Also very important is that less important for HPC applications, but much more important for general IT applications. So basically, you can actually orchestrate various containers into one application, one service. And the prime example is that of that is that you create a container for running a web server, that you contain a different container for running your SQL database, PostgreSQL, MariaDB, whatever you choose. You run a third container because actually that web application which you're running on that web server is going to use a document database such as Mongo or whatever to store logs or to store various things. So basically you need multiple services, multiple software components in order to define your user-facing service. And this, of course, could be done in a single Docker container, but yeah, that's not what people like to do. They like to create a container per service and then orchestrate the containers to work together. There are various ways to do that. Docker comes with Docker Compose, which is fairly straightforward to use. But there are also other, let's say, industrial strength alternatives, such as Kubernetes, and some more modern, which actually I don't know very much about. Because essentially, this is typically not what you want to do on HPC systems. On HPC systems, you will typically want to use things like Singularity more in a, say, standalone fashion. However, if you need to combine several containers on an HPC system, you can still do that using Singularity, and I have an example of that as well. So there is another thing here which is called Shifter, and that has been developed for quite a while. It's actually at NERSC, another big HPC system in the United States. And they've developed this in order to bring the advantages of containers to HPC systems. It's pretty heavyweight, and you also need a lot of cooperation from the HPC support team that runs your specific cluster. So yeah, we decided not to go for Shifter. Okay, so there is one new kit, well, new, not really. So as I already mentioned, Singularity started out as an open source project. Then became a commercial product at Skylabs, but some people did not appreciate that, and they took over the open source project. And of course, for branding reasons, they had to change the name. So basically, that is what is now Aptainer. So Aptainer is sort of very similar to the commercial Singularity, but open source. So I'll very much try to always use the term Aptainer, but keep in mind, if you look at all the documentation, all the use cases, and so on, Aptainer is, for all practical purposes, Singularity. And that is also what we support on, as far as I know, all VSC clusters. Okay. So, right, containers, I already gave you a lot of reasons, perhaps, why to use it in IT, but why use it in HPC? Because, of course, this is about HPC. This is definitely not about web servers and so on, although that can be useful from time to time on HPC, so I'll mention an example. But, okay, so why would they be, why are we talking about this in the first place? So I would argue that containers are very useful. So why? Well, some dependency chains are pretty hard to resolve. You really have to install quite a lot of stuff in order to get things running. An example, at some point, one of our users asked me to install Grace. Okay, you may not know Grace. In fact, I'm hoping you don't know Grace. Okay, if you're a bit older, then you might know Grace and hopefully you forgot about it. Actually, it's not a bad application. It's an application to, in a very convenient way, create scientific plots. And it's absolutely nice, except that it depends on a GUI toolkit, which has seen no maintenance since 2007. Grace itself has not been updated since 2005. So you see where this is going. This is not easy to install. And frankly, that toolkit is, to my knowledge, not used by anything else except Grace. So yeah, okay, the user had some arguments, good or bad, to still keep on running this very old application. So it could be installed using a container, because it was fairly easy to install using on Ubuntu using apt-get, and hence I provided the person with a container and he could run Grace on an HPC system. Okay, is this a good use case? Well, it was definitely a nice one for me because it saved me a lot of trouble. Another application which I've seen is running very old software that is actually only working correctly with 32 bits architectures, libraries. And typically, those are not installed on HPC systems, and typically we don't even want to install them on HPC system because people might use them accidentally, and that will really kill performance. So yeah, 32 bits, yeah, we don't want to do that. But still, there is software out there that, for whatever reason, yeah, okay, bioinformatics, of course, you still need to run because it's a gold standard or whatever. So yeah, should be handled somehow, but preferably not by installing 32-bit libraries on an HPC system. So again, a very good use case for containers. Also, what it's used for, and there is a nice example of that as well on Tier 1, and that's actually a very old example. So there is a question about compatibility between Singularity, commercially, and Aptainer on the other hand. So for the moment, mostly the answer is yes. Will that still be the case in the future? That is not necessarily the case, because the development tracks are now starting to diverge. So basically, the commercial singularity is going very much into the very strong support of OSI, so the composability of container components, which is nice. Aptainer, on the other hand, is not moving much in that direction. So, as far as I know, Singularity recipes specifically developed for commercial Singularity will still build on Aptainer and vice versa. But the way they are built is already different, and that does have some implications, but is not too relevant in our context. How long this will remain the case is hard to say, because, yeah, okay, Scilabs is a commercial company, so what direction they will take is not necessarily public knowledge. So I don't know for the future. Okay, so an interesting example was, and that's really a long time ago. Actually, that's when I started to look at containers, because again, we needed to solve a problem. And that was a commercial client on tier 1. Tier 1 compute, I have to say nowadays. Back in the days, it was just tier 1. But tier 1 compute. And that is a company called E3. Yeah, it's E3. And what they are doing essentially is, you are a company, an energy company. You want a wind farm somewhere, and you want that somewhere to be optimally chosen. So what they basically do at E3 is say, well, okay, that's your target area. Okay, we will use weather models in order to predict where your wind farm is going to be most efficient. And of course, there are a few things in that sentence which point to heavy HPC use. Weather prediction, yeah, right. You really need HPC systems and pretty much compute time in order to weather predictions. And the other phrase which you probably picked up on is optimal. So that means that you're not going to do that for just a single time. You are going to do that multiple times. So yeah, it's pretty heavy HPC. And of course, they did a proof of concept. Well, of course, they did a proof of concept on tier 1 compute, and it worked nicely. But they are a company, so they offer these computations, okay, the result of that, to their customers. So that means that they need quality of service guarantees, 24/7 access, 24/7 support, that kind of thing, which is stuff which we at the VSC do not provide. We don't ever sign a contract with the quality of service like that, because we can't give it. Give us 3 times the money we have right now and we'll do it. Otherwise, no, we're not going to do that. So basically that means that commercial companies, for their deployment of their production code or their production applications, they normally don't do that on tier 1. They do that elsewhere. And that elsewhere, in case of E3, was actually Amazon AWS. So they needed a workflow that would scale from tier 1, well, actually from their own systems, because they had workstations, maybe a small cluster, but I don't think so, can't remember. But it should work in-house, it should work at the VSC tier 1 compute, and it should work in the cloud. And later on, also in multiple clouds. So that is, again, a very nice use case for containers, and we actually solved their problem using that. And they were actually the first HPC users on our systems to use Singularity, well, what is now Aptainer. Okay, so that's all very nice and very good motivations to use containers, but they do pose security risks, potentially. So if you look at Docker, it actually requires root privileges in order to run containers. Okay, Docker is working on that. There is Podman as an alternative, but still, there are security risks. So that's basically because some privileges need to be escalated. And that is always a risk, even if it is well implemented and so on, you're still potentially vulnerable because someone might have made a mistake. There might be a bug somewhere which still allows for escalated privileges when that should not happen. So, okay, that is not so interesting. Also, they can potentially have access to the entire file system, which is really not something you want on a multi-tenant system such as an HPC cluster. So that is why at the time Singularity, now Aptainer, has been developed. So basically, this is a bit about the architecture. Let me just summarize the important points. So essentially, a Singularity container runs on top of course, your Linux kernel, but it has really nothing to do with the rest of your system. So it runs kind of independently of that. So basically, you can view the Aptainer processes as additional processes on your system, but they run within a container. So essentially, the only thing which gets out of the container are calls to the Linux kernel. The Linux kernel runs on top of the physical hardware, on top of the actual bare metal, and basically that means that that works nicely. So in a Singularity container, there is no root. So the root user does not exist. So in a Singularity container, even if you install sudo and you execute sudo, it's not going to work. You can't do that. And that, of course, is something that we as HPC providers like quite a lot because, yeah, we're not going to let you be root under any circumstance in any conceivable universe. So basically, this is something we really, really like. And to my knowledge, there has never been a security problem with Aptainer. So for us, this is reassuring. And for us, that means that we can happily allow people to use containers, Singularity containers, Aptainer containers on our systems. Okay, so what is the distinction between Docker and Aptainer? Well, Aptainer has, at least for me, and in a sense also for scientists, one big advantage, well, several actually, over Docker containers. So from my point of view, and feel free to share or not share that. So from my point of view, it is nice because it's a single file. So yeah, it's a pretty large file, but a single file. And everything's in there. So all the OS components which are required to run whatever is in your container are contained in it. System libraries, the libraries which you require for your application. The application itself can also be in your container. If you require data in your container, you can do that. Should you? Different discussion. There may be use cases. In some other cases, it's probably not a good idea because it will increase the size of your container, which is something you also do not necessarily want to happen. But I can imagine that there are use cases for that. For instance, if that data is very application specific, And now I'm thinking, for instance, of quantum chemistry applications where you need a lot of data just about chemical components, about chemical properties of molecules and atoms and so on. Bioinformatics, where you need a library, preferably not really, really huge, because otherwise you will have trouble. But in general, it's possible. Why do I think that that is a good idea? Well, essentially, reproducibility. Because the nice thing is that given that that's a single file, I can store that somewhere and I can rerun it in 6 months' time, in a year time, whatever. It is still going to work. And it will still contain the exact components which I used in order to produce my paper, for which I got a referral report yesterday requesting that I would redo these and these and these and these computations. Okay. For people from KU Leuven, but it also goes for people of other VSC that use VSC hubs, you may sometimes have the misfortune that we actually have to upgrade the operating system. Yeah, we need to do that because of security reasons. We can't keep an old system, an old operating system around for ages. And that is unpleasant because that means breaking changes. So that means that if you do not use containers, you will have to potentially rebuild your software. And given that that is on another version of an operating system, or still worse, on a different operating system, that might be somewhat challenging. And you may or may not have tests in place in order to see whether your software still does the same thing. Okay, usually it will, maybe it won't, but you don't know. That's very nice if you packed everything in a container, because your container is going to run identically as on the original operating system. So that's kind of cute. So how do you create a container? And we'll do so in practice later on. You can essentially do that on any machine. Yeah, well, okay, any Linux machine. Operating system, don't care. As long as you can run Apptainer there, nobody cares. Oh yeah, well, basically some software has in fact been deployed as containers. You load a module, and what you are actually going to run is indeed an application which has been packaged into an Apptainer container. Nowadays, I'm not so much into software installation, so I don't really remember which software packages are installed into containers, but there are definitely a couple. So you might actually already be using a container without actually realizing it. Because I will also show you later on that it is quite transparent. And that's a different use case for containers. One that I personally use quite a lot, containers for development. But this I'll show you later on. Okay, so you can create your container anywhere you want, as long as it's Linux. Operating system, nobody cares. Oh yeah, macOS is also sort of an option as far as I know. I don't have a Mac, so I can't really experiment what works and what doesn't work, but I think that containers are now native on macOS as well. Typically, it requires root privileges, but not always. So basically, you can, in fact, build a container on an HPC system without requiring root privileges. It can also be done remote, and I'll show you that as well. So basically, you can build a container on Scilabs, for instance, and then deploy it on your system. That's also possible. So that's the creation thing, deployment. So basically it will run on any Linux machine as long as Obtainer is installed. And to run Obtainer containers, you do not need root privileges. And that's, of course, what we as HPC teams very much appreciate. Okay. So you're on a Linux system. How do you get Obtainer? Well, very simple. You can just use a package manager. You may have to add an additional repository, but you'll find instructions on the Obtainer site. So it's very easy and it's very painless. I do maintain my version of Obtainer here using opt. This is an this is, well, as you probably guess, because I'm using PowerPoint, this is a Windows system. It's my Windows desktop. But of course, who does scientific computing under Windows? Windows is very nice to make PowerPoint presentations and to browse the web. It's, well, okay, I'm going to be contentious here, pretty useless to do anything related to science, except not even to write articles, because, yeah, you use LaTeX. So, well, okay, you don't. You might use Word, and then suddenly your Windows computer gets useful again. But the very nice thing about modern versions of Windows, and then I'm talking primarily Windows 11, but also Windows 10, if you're still stuck with that, you can actually install WSL, so the Windows subsystem for Linux, and you can happily run Ubuntu, for instance, but also several other operating systems on your Windows system. You have a terminal, you can use X applications, whatever. It's really pretty nice, and for development, I use it all the time. And of course, I also installed Obtainer. So basically, as you can see, version 1.2.4 of Obtainer here, we can have a look what is currently installed on the cluster. So let me quickly go to the cluster. I'm going to the KU Leuven one, but of course, okay. Okay, so they're pretty much up to date, so that gets updated automatically using Puppet most likely. Mm. Okay, this was really, really stupid. I closed. Oh, I thought it was. Um, I thought that was just the tab in which the authentication thing happened, but of course it also contained my Toledo session. So, okay, back to sharing things. All right. Right, let's get back to my terminal. So basically, yeah, we actually happen to have the same versions both on my own Linux subsystem and on the cluster. Might be different for your cluster, whether it's in Antwerp, Ghent, or Brussels, but still normally I expect that Obtainer is supported everywhere, or at least installed everywhere. Okay, so You can also, if you want or need to, build Obtainer from source. There are a few dependencies such as Squash FS and Fuse, but apart from that, it's fairly straightforward to do. But frankly, I don't think there's any need because it will be available through package managers for all major operating systems. Back in the days when I used Manjaro, it also worked pretty nicely. Okay, so let's go through some practical things. How do you create images? Well, basically what you need is a recipe file. And that recipe file is just a text file, so that's pretty straightforward. It has its own format, which may or may not be a good thing. You could argue that something like YAML or JSON or something like that would be a better idea, but okay, this is pretty readable, so in that respect, why not? So the first thing you need to do is to set the base operating system. So what kind of image are you going to make? So in this case, for Bootstrap, we're going to use dbootstrap because this is a Debian thing. And this is for a fairly recent, not extremely recent, version of Ubuntu, so Focal at the time, so that's a 20.04. That we can specify by just giving the label, or you can also specify version numbers and so on. And you also specify the URL where the operating system can in fact be downloaded from. Okay. The Bootstrap application needs to be installed on the host. As far as I recall, that is the case now automatically for Ubuntu, but if not, you can just install that easily using your favorite package manager. Okay, so for Debian-based systems like Ubuntu, like Debian itself and so on, you can use the Bootstrap. If you have something like CentOS or Rocky or whatever, then you can simply, as Bootstrap, use Yum. So in the second case, I'm going to install a CentOS, CentOS 7 to be precise, and the Bootstrap application is Yum. Okay, and you here also specify that you want to include Yum into the image. Okay, so that's always the first step of your recipe file. But of course, there's more to follow. You can also bootstrap from Docker. So if you have your favorite Docker image that you have been using, and now you say, oh, okay, I want to use it on an HPC system, but those bloody system administrators refuse to let me use Docker. Yeah, we do. Then it's very simple. You can just turn your Docker your Docker container into a into an Obtainer image. So the only thing to do is to Bootstrap here. So basically, you need something to install your operating system. And so basically, Bootstrap means that that is a very small application that will be able to contact the servers where your system images are stored, and they can access them and install them onto a file system. So that is basically, you can compare it a little bit to the installer which you're going to use if you install a Linux operating system from scratch. You also need a small application in order to get that done. And the core of that application, because typically that is for a Linux distribution, it will be backed into some either sophisticated or primitive GUI in order to do an installation. But at the heart of that, there is still a Bootstrap application, which you can also use from the command line, and which says, well, okay, this application that is going to contact the server that contains the OS images for that particular operating system and is able to do a couple of things like format your hard disk so that it can actually have a file system it can work with. It will also do things like initializing your bootloader, so the small piece of software that runs even before your operating system is going to launch, and that will just check, okay, which boot records do I have, which operating systems are installed on the system, and which one is default to start. So all of that can be done by a bootstrap application, which would be yum for CentOS, which would be dbootstrap for Debian. So that's what a bootstrap thing is. Not a big deal, in a way. Well, not a big deal. It's really a big deal, but not something that you need to worry about, because yeah, it does its thing, and you don't have to think about it, what it does. Well, you do have to think of what it does if you're installing on an existing system. If you're installing into a container, into an image, you don't care. But to get back to Docker, so basically, if you want to use Docker, one of the things, let me just check whether recordings are still made. Yeah, so I'm still recording. All right. The thing you need to do is to specify Docker as a bootstrap, and then you can just specify the Docker tag from which you want to create your container. So that's actually very nice, and that means I'll give some examples that I don't really care whether or not I can use Docker, because I can always, I hope it's just you. Are there other problems? Yeah, okay. So I would suggest just pop out for a second and pop in again. That is likely to solve the problem for you, the sound problem. Okay, I'll go a bit slower to give Said the opportunity to try and fix his issues. Okay, so this would be for a Debian. So basically, Jesse is a somewhat older version of Debian, and you can run it. Okay, all my examples are for pretty old versions of operating systems. Okay, that's not because you can't have modern versions, no problem. I mean, you can have anything you want, but basically these slides have been made a few years ago, and yeah, who cares? Okay, so essentially that means that any publicly available Docker container can in fact be used in order to build an image. So that takes away the issue that Docker is not really supported on HPC systems. Well, that they're not supported on HPC systems, to be very precise. Okay, so any public Docker container, but also containers in private repositories. But then, of course, you need to specify a token to use in order to access those repositories. So KU Leuven, for instance, has its own artifacts repositories, where artifacts are lots of things, but including Docker stuff. And of course, you can use those in order to store your own Docker containers, and also to retrieve Docker containers. Okay, let's continue with the recipe file. So we specified our bootstrap, we specified our base operating system, so the operating system which we want to run in the container, and then we can do a number of things. So sometimes it can be useful to execute a command on the host. So for instance, you might want to actually create a directory. And for that, to run things on the host, you can use percentage setup. So this is basically a section in your recipe file with commands that will be executed on the host. And in this case, a sample directory is being created in the Singularity root FS. So this is being done from the host into the file system that is part of your image. Okay, you can do that in a different way as well, but the setup section can be useful for that kind of purpose. Then there is also the files section, and that can be used in order to copy files into the image, and that will be done as soon as the base operating system is installed. So in this case, we want from a host directory samples, copy a couple of files into the directory you created in the setup section. So these are the host files and directories, and this is the destination. So the files section just follows the semantics of the Linux copy command, Linux cp command. So you were very familiar with that. So basically, this is nothing new for you. And of course, you can have a single file section or you can have multiple. Doesn't matter. Depending on how you write your recipe, it can make sense to put everything into a single section or into multiple sections to structure your recipe better. Okay, so basically, another thing which is very important is the post section. And that is post with respect to the bootstrap phase. So basically, that is everything that happens after your base operating system is installed. And that can be software installation. And yeah, you can do that through a package manager. So if your image runs a Debian-based operating system, you can start installing software into your container using opt. Or if it's CentOS-based or Rocky-based, you can use yum, no problem. So it can also download a GitHub repository, well, clone a GitHub repository, or download a tarball, extract that, do a configure, make, and make install, or a cmake, whatever. All possible. You could even consider using easy build in here. It's also possible. So for instance, for Ubuntu, again, we have a post section. And here we fiddle a little bit because on some versions of Ubuntu, you may need to add the universal repository. So this would do that using set. And then we can do an apt-get update followed by an apt-get install. And in this case, the example is for that infamous plotting application, Grace. Okay, it's useful to add the -y flag here. That mainly says, well, okay, you're not going to be asked for confirmation. And that is very useful if you, well, you should try to make your recipes independent, in such a way that they can be done unattended, so that you do not need to give confirmation for whatever. That is always quite useful. So that's why it's a very good idea, best practice actually, to add a -y flag. And yum actually has a similar thing, so it also has this -y flag. So remember, everything which is here for Ubuntu is for anything Debian based. That means you can use opt. For other base operating systems, you might want to use yum. So don't use yum on Ubuntu. That's not going to be a big success. Don't use opt on CentOS or on Rocky. That's also not going to be a big success. So that won't work. Okay. You can add applications, you can also add environment variables. And that's actually rather nice, because that means that when your image is going to run, then those environment variables will be available. So that can be useful as well, and that's why we have the environment section. Okay. Another thing which is nice is the run script section. So that is the action that is going to be taken for if you do a Singularity run. And run script can, for instance, be, again, for our Grace example, this will just start Grace as an X11 application. No, not as an X11 application, as a terminal application, actually. So that means you can, in fact, just run a container. Actually, if you make, well, okay, an image. If you make an image executable, then it will actually execute this run script if it's given. Okay. I'll also give an example of multiple applications. I don't have it on the slides because, okay, I'm not really convinced that it's, well, it can have its uses, let's put it that way, but I don't think I ever used it in practice. So yeah, it can be done, but it's not necessarily very useful. There are other ways to do it which are more standard and which I personally prefer. Okay, I really have to change Singularity everywhere by obtainer. I didn't do that yet because the last time I gave this presentation, we were still in the transition phase between Singularity and obtainer. I already had obtainer on my systems, but they were not yet on the VSC systems. So, but now, almost a year later, that is the case. So I should really update the slides. I hesitated last time, but I should do it now. Okay, what can also be useful is to add a test section. And that is actually what is going to be executed when you do obtainer test. So that can make a lot of sense, just to do a sanity check whether your image works as expected. And in this particular case, it's a fairly trivial test. It will just run Grace and print the version. Of course, you can go much further here. You can even include functional testing, for instance, running an application with a small data set and checking whether the results are as expected. In that case, of course, you would need to store input and output data for this test within your container. Okay. You can also give labels, which may or may not be useful. What I would typically add is a maintainer and the version. That can be useful. You can do other things. You can give hints about, for instance, what this application is about and so on. So a subject domain like, okay, bioinformatics or something like that. But I don't use it that much. I consider maintainer and version useful. Okay, and of course you can also add a help section, and that is basically going to be printed when you do a Singularity run with the -help option. So again, that is useful for giving documentation. Okay, so all of this has to be put together. So here a number of things have just been added, not everything which I mentioned, but the most salient things are here. So basically you've got your bootstrap, always the first thing. Then you have any number of file copies. You have post, which installs some additional software, and you have run script, test, help, etc., etc. So this is just a single file. It's a text file. So you can just store that into your favorite GitHub repository that stores everything you need for your project. That's nice. Okay, so that was easy. Let's perhaps look at some other example. Let's increase the font size here a little bit. Let's see whether there's something exciting here. These are all fairly old examples. Maybe the CUDA one is nice. Okay, so what I'm doing here as a bootstrap would update be based installation. Okay, Conda versus containers, basically. Well, it strongly depends. So I will get into the issue of performance with respect to containers later on when I talk about best practices, and there is a lot to say about that. And similar remarks can be made about Conda. So, okay, forget for a second about performance. This is a discussion for later. So, how do Conda and containers compare with in other respects? So, you use Conda typically in order to easily install software. That's one thing. You also use Conda in order to create environments that you can share with other people and that allow you a degree of reproducibility. In the sense that once that I have created my Conda environment, I can export it as a YAML file. I can also get a more detailed specification file, and this I can put into a version control repository, which is nice because that means that I can reproduce my environment. So that is sort of reproducibility. Yeah, you notice that I'm using sort of. And of course, I can also share it with other people because if I give them the specification file, they can reproduce that Conda environment. So yeah, that's a good thing. And that is an excellent first step with respect to reproducibility. There are a few issues. One of the issues is that sharing Conda environments between operating systems can be somewhat challenging because a specification file is not going to cut it because that is typically specific for a certain operating system. Maybe just as an aside, because it might not be entirely clear what I mean by a specification file. So, come on, why is this not working? Okay, now it is. So let me give you an example. So for any training I give, they're usually, well, if it's Python related or uses Python tools, there typically is an environment file which describes the environment which you need in order to run all the scripts, whatever that are, well, in that training. So what I also do for that reason is making available two files. And that is this one. And that's a specification file for an environment, and it's a very detailed one. And as you can see, that from the names which are here, that means this is specifically for Linux. So if you're on a Windows system and you run Conda there, this is not going to be terribly useful. Well, it won't work, to be very concrete. So this is really a recipe for reproducibility because as you can see, all the details of the libraries, the Python packages, etc., are specified in great detail up to the patch level and the hash key and so on. The whole thing is very strictly specified. So this gives me very good reproducibility. But I can't share this with a macOS user. I can't share this with a Windows user. Okay, so yeah, I've got very reasonable reproducibility, but I can't share it. Well, not with non-Linux users. Okay, I have an alternative, which is the environment.yaml file, but that is much less specific. Okay, yeah, I took away the version numbers here because I want this to build in future as well. But still, it would just give me the versions. Let me just show you where that comes from. So that is the result of a export from history. And that's what you get for this environment. Ah yeah, the version numbers aren't even there. So basically, this gives me very good shareability. I can give you this file. You can install the whole thing, the whole environment on Linux, on macOS, on Windows. It will work. However, this is not reproducibility. No version numbers, no specifics for operating systems, and so on. Absolutely no mention of underlying libraries. So yeah, this is shareable but not reproducible. And there is, with Comma, not much middle ground. So I've had several times the problem that I created a Comma environment, that I needed to recreate it a year after creating it, and it was just impossible. It just wouldn't resolve the dependencies anymore. So I had to go in and tweak my environment file, my environment specification file, in order to get it to actually create an environment. So yeah, with obtainer containers, this is not the case. I mean, I can run any obtainer container which I ever made, and I can still run it. So that is really reproducibility. And also I can share it with anyone who has access to a system that runs Obtainer. So that's it, trying to address that question. So the question is, how important is flexibility, which you have much more of with Conda, with respect to reproducibility, which you have much better with containers? Okay. So I was showing you yet another recipe. So this is a very simple one. It uses Docker as a bootstrap, and it's going to give me a development environment for CUDA. This is, by the way, a very old version, 11.4. Yeah, that's Middle Ages. We're at 12.3 now, but okay, whatever. And that is actually a Docker container which is made available by NVIDIA. Okay, so that will be my base operating system, and that also means that I've got all development tools for CUDA within this image. But of course, I want a little, of course, I would have to check what operating system this is. And it is something that is, what is it? I don't remember which one it is. But obviously, it's something for which I need to use the yum installer. So that's something that you need to figure out first. That's typically in the documentation as well. And then I want to install some additional things. For instance, within my container, I want an editor. And I also want a pager, because they're typically not part of the base image. And then, as a run script, I just want bash. Okay. So, how do we, I'll give some more examples of recipes later on. So how do we build this image? Well, what is a build? Let's first talk about that. So a build is actually creating an image. Okay, so basically that means kind of preparing the file system, then installing on that file system the base operating system, and in case of Docker containers, everything it comes with. so also software that is included in that base image. And then you can install, then all software which you specify in post is going to be installed. All the files which you want to copy into your image from the host are copied, etc., etc. Your environment is set, blah, 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 the whole shebang. Okay, so how do you do that? Typically, you use sudo. So in this case, I would do sudo. Okay, let me build something that we can actually use, because this CUDA example is a little bit old. So let me go to here. I'll talk about this in more detail later. Okay, let me do that later. Okay, so typically you do sudo obtainer build. You specify the name of your image, and the extension for that is .sif. So that stands for Singularity Image Format. And then you specify the recipe file. Okay. I always mix them up. So when I've not built the container for a while, I'm going to always do obtainer build my definition file and then my image file. But Singularity is, or obtainer is kind enough to warn me that I'm doing stupid things. So it will say, okay, are you really sure you want to do this? And the answer is always no. Okay, so the image is put first and then the definition file. Okay, so for this you need to have sudo rights, which means that on a cluster you can't do that, because we are not ever going to give you sudo rights unless you join the team, and then you can be an administrator. Okay, but obtainer actually supports the fake root flag, and that might have to be a double dash. I need to check that. That might be a typo. Basically, that means it will pretend that you're root. And up to this point, in fact, I've never seen a counterexample, so this always seems to work, which is nice, because that means that I can just build my container essentially wherever I want on any system, even if I don't have root privileges. Okay, so this unfortunately is nowadays less the case, but still a little bit applicable. So basically, if you change the definition file, then if you're lucky, only those sections which have been modified are in fact re-executed when you build the image. It's, yeah, for some reason to a lesser degree nowadays. So this is an advantage which kind of doesn't exist as well as it did in the past. Don't know why. Okay, so there are several types of images. Default is SIF, but you can also have squash FS as a type, and that basically means that it is in fact a file system which is compressed and which is used using views. So basically the file system that exists in user space. That is read-only. You can also have a writable file, but then you really need a sudo build. Otherwise, that's really not going to work. And that can be, for instance, X3 as a format. It's also possible to use sandboxes. I never use them. In my opinion, they're counterproductive. But I'll come back to that when I talk about best practices. So I'm not a fan at all. But it basically means that you get a Singularity image that exists as a directory structure on your file system. And that basically means that you can go in and manually copy in stuff, manually change stuff to your liking. And that may sound attractive, but it's not a good idea. So I'd really not recommend it. I know that there are a lot of people who are very much fond of it, but yeah, I don't think it's a good idea. Okay, properties. So typically an image is read-only. You can make it read-write by running it as sudo, but yeah, again, not a good idea for reproducibility mainly. So, okay, is that a good idea? I don't think so. So typically, to be honest, I just use CIF images and I'm done with it. I mean, what you can also do is a multi-stage build. And that is interesting because if you're building software in your image during the build phase, then of course you need a lot of libraries. You need a lot of tools. For instance, you might need CMake. You might need several development versions of libraries, which take up more space than runtime libraries. You may need other tools just to build the software which you want to deploy in the image. Okay, that's cool, but that takes up space. That makes your image a lot larger because it needs to have this CMake, it needs to have all those libraries. It needs to have the compilers. Do you want that? Well, you don't need it because the only thing which you want your container for is to run the application. The build process is just, well, a necessary first step. So it will take up space. It will increase the size of your image. Okay, but it also means that it increases the time to load your image, and it will also potentially increase the memory footprint. So basically, that is a situation which you may want to avoid. If you need to load a container or to run a container several times concurrently, then of course that hits the file system more if the image is larger. So basically, that's why multi-stage builds have been introduced. And that basically means that you, in fact, build several images. For instance, one which is doing the build of your software. Okay, that produces a number of artifacts, for instance, a number of shared libraries specific to your application. It produces a number of executables. It might produce some scripts, etc., whatever. That is happening in the build phase. For that, you need, for instance, CMake. You need your compilers, etc., etc. Okay. Then in the next phase, in the next stage of the build, you use a much smaller image without all the build software, and you just copy the artifacts of the build process in the first stage to the deployment stage. And that results in a much smaller image. Also, you can, in fact, if you want, use different versions of the operating system in order to build on the one hand and to run on the other hand, or to deploy. So let me give you a few examples of this, and let's do an experiment. So let me go to multi-stage. Okay, and let's have a look at the definition file. So let's first have a look at the single stage file. So it's pretty straightforward. Again, we bootstrap from Docker, and we are going to use Alpine. Alpine is an operating system that is really small. Okay, so I have a source directory here, at least I hope I have it, which contains a number of files. We'll have a look at it later, but I want to copy the source directory, which is on the host, into the image. Okay, and I'm just lazy, I'm just putting that under the root in the source directory. Okay, then in post, I'm going to use the package manager specific for Alpine, and that's APK. And I first do an update in order to get the latest definitions for whatever is in the package repository. Then I add make, because I'll need that to build my software. I need a C compiler. I need muzzle dev. That's development stuff specific for all Alpine. I don't quite. I should have added a comment here. But you really need it if you want to build software with Muzzle, with Alpine. It took me a while to figure that out because nothing worked until I added this after some Googling. Okay, so I go into my source directory. I'm going to execute main, and then I'm going to do something that you might find very weird, but I'll come back to that in best practices. So I copy the executable, which is hello world, into the bin directory. Okay. Now let's have a look at what the, well, let's build that. Okay. So I'm going to be lazy. I'm going to do sudo obtainer build. Okay. Let's call that single.sif. And okay, for some reason it doesn't. Tab completion doesn't work. Don't know why. Okay, so let's just do that. I did that as sudo, so I give my password. Okay, so as you can see, this goes pretty fast. The Docker image is really small, so that's pulled in very fast. Then you see that appk is working. It's installing libgcc, libstd c++, etc. So that's the Muzzle dev thing. It's installing a few libraries, and then GCC. Make should be somewhere here. I don't see it, but it's probably, well, I don't know where it is, to be honest. Should be there. Okay, anyway, it seems to be installed. We go to the source directory, we execute make, you see the make output, and we copy to bin, and we're done. Okay, great. That was easy and fast. Let's do obtainer exec. That's a different way to run a container. That basically means that I can specify what I want to run, because in the recipe there was no run script. Okay, so exec and my container zip file, and then what I want to do, okay, I want to run hello world. Okay, so that works, and by the way, that seems to be, I had totally forgotten, but that's apparently an OpenMP application. So great, let's have a look at the source code. And indeed, it's an OpenMP application, so stuff happens in parallel, fairly trivial. This is just a very stupid hello world in C for an OpenMP application. Okay, never mind. But as you can see, and that's actually pretty cool, my applications in my container can be OpenMP applications, and indeed, it picks up from the host operating system when it's running. So basically from my hardware, if you want, from the kernel, it picks up that indeed this system has 16 cores. As you can see, it has 16 cores, and I can just run this. So if you indeed want to use obtainer to do this, omp num-threads is just going to be passed to the container environment, and now the thing runs with 4 threads. So all of this works. So basically, if for whatever reason I need to package an OpenMP application into a container, I can still easily control it using the normal environment variables, which I set on the host, which are propagated into my container when it's running. Okay, I am going to silence my colleagues because they are really getting on my nerves. Let me put my status to do not disturb. Okay, right. Sorry. There's only so much chatter I can deal with during a training. All right, so let's get back to the other recipe. So let's check the size of this. Single sieve. And as you can see, yeah, okay, that was stupid. I also need the L option, of course, otherwise you don't see this. It's 47 megabyte. Okay, not too bad. You can live with it. But let's have a look at the multi-stage recipe. And then you see that it's quite similar. Again, I'm bootstrapping with Docker. The Alpine image is the same, but I specify something additionally. I specify a build stage. So everything up to the next bootstrap from and stage thing is going to happen first in the first stage, which is build. And actually, that is to a very large degree the exact same thing as we had before. The only thing which is not here is copying the executable to bin. That's the only thing which is missing. So in the first stage, app-k will install make, GCC, muzzle-dev, etc., etc. However, in order to run these things, to run the application, I don't need make, I don't need GCC, I don't need muzzle-dev. I even don't need the source code. So basically, I'm now in the second stage starting over. I'm again bootstrapping. So again, Alpine will be installed. It's going to be a clean installed. And now I can copy the executable, which I created in the first build, in the first stage. So the build stage. These things are the same. And I'm copying from source hello world application into the bin directory. And note that this file here does not exist in the runtime phase. It only exists in the build phase. So basically, I'm copying from one build phase to the other. Okay, let's also execute this. Build fake root. Let's try it this way. So multi-sieve and multi-stage dev. No. So no, I'm not copying from the host. I'm copying from the previous stage, the image in the previous stage. So this application hello world does not exist literally on the file system of my host. It's not there. It only exists within the file system associated with the first build stage, with the first stage, which is called build. So that's why, let me go back to the recipe. There is here files from build. So that's the salient point here. It's going to copy the result of make, so the application, and it's going to copy that from the stage, which is called build. So this build here is that build here. Okay, so let's run this guy. Well, let's first have a look at the size of the images. Okay, so the single stage build was 4.7 megabytes. The multi-stage build is just 3 megabytes. So yeah, that's pretty impressive. It's a factor of 10. Okay, do you care in this particular case? Maybe not. But you can imagine that if you really need a lot of stuff for your builds, that you would like to trim that down a bit. And that's why multi-stage builds are quite useful. Okay, so as you can see, yeah, no, I should have added a run script. I should do that next time, but okay, never mind. Let's run this thing. So exec multi.sif, and what I want to run, of course, is hello world. Normally that should be my path, so I should be able to do it this way as well. Yeah, it works. Okay, let me do something else. I want to go into my image interactively. Now, which shell does this thing have? I think it's been just plain old shell, so no bash. Yeah, okay. So now I'm interactively in my container. So let's have a look at the contents of the root directory. And as you can see, there is a source directory here. So this is the single stage build, and that contains the source directory. So you will see, for instance, here the makefile and so on. The executable is not here. Why? Yeah. Yeah, that's weird. Why is the executable not here? Did I? No, I didn't move it. Okay, don't know. A little bit puzzled. Anyway, so this is the single stage container. Let me get out of that. And let me go into the multi-stage container. So same, but different. There is no source directory here. So that source directory, which contained the executable, only existed during the first stage. In the second stage, no one created a source directory. The only thing which happened was that the executable got copied from the first stage into the second stage. And of course, you can have as many stages as you like. That is up to you. I think that the most complicated example I ever saw was 3 stages, but okay, that's even marginal. Normally you do only 2 stages, if you do stages at all. If you look at the obtainer documentation, you will in fact find very few examples of this. So in a research context, this is clearly much less done, but it's not a bad idea to think about it at least. Let me give you another example. Conda. Now this gets interesting because we had a question about that. Okay, let's have a look at the environment file. So this is the Conda environment which I want to create. As you can see, it is really exciting. It contains NumPy. Okay, so this is a very small one, just for demonstration purposes. Okay, let's have a look at the recipe. All right, so yeah, I should remove this comment. So yeah, I'll come back to this. So this is a recipe file which was partly generated automatically. So that's why it looks a little weird from time to time, but never mind. Okay, so we bootstrap from Docker, and I'm going to bootstrap from a specific environment, again based on Alpine, but that has Miniconda installed into it. So that is kind of convenient. And I have a build stage here. So this is the first stage. Okay, this is basically done automatically. Don't worry, you can forget about this first post, it doesn't matter. And then we do a conda install. And basically what we install is a package, Python package, which is called conda pack. Why we need it, we'll see soon enough. But basically it comes from Conda Forge. So if you're familiar with Conda, this is not really anything new. Okay, so of course in my image, when I'm installing stuff using Conda, I'll need the environment file. So we have a file section, and that copies the environment.yaml file, which I just showed you on the host, into the image. And I'm lazy, I'm just copying that into my root directory. Okay, then next we're going to create that environment. So that's conf env create. The name of the environment can be whatever, I don't really care. And I'm using the environment file, which I just copied into my image to use to define the environment. Okay, so environment is created, and now I'm going to pack that environment. So that's why the conda pack stuff was installed. I'm going to pack the environment into a table, so into a tar.gz. Okay, so in my first stage, I created my environment, and I created a packed version of that into a table. Second stage. Okay. Again, Bootstrap Docker. Now I'm using a different operating system. I'm in fact using Debian, Bullseye, and the slim version of that in order to have a smaller image. Okay. This is the runtime stage, so the second stage. All right, forget about this. Then we have files from build. So I'm going to copy the table from the build phase, so my packaged environment, into the image, which I'm building now, so the runtime image. Okay. Then I'm going to create an environment directory. I'm going in there, and I'm going to extract my environment there. Okay. Going to clean up. I don't need that tarball. And I'm going to unpack my environment. So Python with this conda unpack script is going to prepare my environment, well, to make the unpacked tarball into a proper working environment. So by the way, this is a very nice trick if you need to move an environment for whatever reason. Use conda pack, and it will actually do the right thing. Okay, and then finally, I'm setting the environment variable to include that Python version. Okay, so let's see what that does. So never tried this with the fake root, but let's give it a try. I expect it works, but who knows. Okay, so let's call the image conda sif, and let's do the conda recipe thing. Okay, so it's fetching the Alpine operating system with the mini conda thing. Okay, unpack layer, blah blah blah. Then it's running conda install. So for the conda pack thing, and as you can see, the usual stuff happens. It's downloading stuff, dependencies. It's now creating my environment. So that's the second step, based on the environment file, which was copied into the image. This, by the way, is why I use Mamba rather than Conda, because that's like a million times faster, but okay. I was too lazy to check whether there was a image file with Mamba installed. Probably there is. And also, okay, I don't care whether it takes a while because yeah, you only do this a couple of times, and meanwhile you drink coffee, you read email, etc., etc. Okay, let's just assume that stuff is happening. We'll return to it later on. So basically, as you can see, these multi-stage builds can be quite interesting in order to reduce package sizes and the image sizes and so on, but also to really fine-tune your image. Okay. The dependencies, yeah. So basically, of course, if you have a lot of runtime libraries, and that's something that I should show you because it's not on the slides and it's rather neat. You can actually do this. So let me go to the obtainer documentation. That should be here, and whatever latest, I don't care. Let's switch off extra contrast because I think for you that's harder to read that way. Okay, so this must be better. Now, what do I want? Multi-stage builds, where are they? No multi-stage builds. Advanced usage, maybe. Oh, come on, I looked at it yesterday. Where is it? Okay, let's just use the help the search function here. Stage. What? Total nonsense. Right. Okay, let's try this one. Multi-stage builds. Okay, so the neat thing is no, I don't see it. Damn. Okay, I'll have to get back to you with that. Because it's something really, really neat, and now I can't find it in documentation. So that is a little annoying. Because I only saw it yesterday, and unfortunately I didn't have time to add it to the slides. But basically it means that if you use a lot of development libraries, you can specify in your runtime image specification that you want the okay, yeah, got it. Okay, yeah, it's not in fact in a recipe. That's the point. Okay, now I remember. Yeah, that makes it less useful anyway, but okay. So basically, what I was trying to say, so of course, if your application depends on development libraries during build, for instance, you use GSL, just to give a trivial example, then basically it also means that you will have to be careful that your runtime image contains the runtime libraries. So that's something to keep in mind. And of course, you can always check. So now I'm not sure whether I did a dynamic build or a static build here. So let's go into the single stage. Okay, different directory, that's not going to work. Not this stage. Okay, so let's try ldd bin hello world. Okay, it's, yeah, I did a static build apparently. Is that the case? Yeah, that's a static build. Okay, yeah, then of course you don't have any dependencies and that point is mute. So that's something to consider in order to kind of minimize runtime dependencies. Do a static build of your software, if you can do that. It's not always an option for each and any application. Okay, so that's about builds. So now we've built and actually already run a couple of images, and I would say it is quite time for a break. So let's have a break until it's now, okay, let's make that 10:55. That gives you almost a quarter of an hour. Let me also put that on the whiteboard. If there are any questions, please feel free at all times. Also during the break, feel free to type in questions. I'll deal with them as soon as I have some extra coffee. Okay. Okay, let's resume. There are a few interesting questions in the chat, so I'll start with those, but just that I don't forget, I'm going to reshare my screen because otherwise when I continue, then I'm talking and you don't see anything, which is not productive. Okay, there we go. And let's go here. Is there something to see here? No, not really, I think. All right, the questions. Right, yeah, damn. I need to switch to chat, of course. Okay, so the first question is, Docker is not allowed on HPC systems indeed, but companies use it. So why on earth can companies use it safely, and is it not safe on HPC systems? Well, the point is that HPC systems are multi-tenant in the sense that on the same cluster, jobs of very different users are running. Even worse, on some clusters, jobs of different users are running on the same node. Okay, so that means that if I'm malicious and I know how to exploit an, escalation of privileges on that system, I suddenly gain access to data of other users. And that's, of course, something that we cannot risk. Also, if you gain root privileges somehow, if you can escalate your privileges, you might suddenly have access to parts of a file system where you normally have no business, in the sense that it's all shared file systems, so they're mounted on compute nodes, which means that if you have root privileges, you can do unpleasant things, either snooping on other people's data or even corrupting things or whatever. So that is a specific problem to multi-tenant systems, systems on which multiple users have access at the same time. So that means that if you are running, for instance, a cloud instance on Amazon or on Tier 1 cloud or your favorite cloud provider, it doesn't matter. It's not multi-tenant, it's just you. So basically, of course, it's still possible that someone maliciously gains access to your instance, and but then at that point your system is already compromised. So whether you're using Docker, you're running Docker or not, doesn't matter anymore, because that person has already breached the security at the operating system level by, for instance, hacking into your web server or doing some malicious things by buffer overflows or whatever. So that is the reason why there is nothing wrong with Docker, as long as you run it safely. That is in an environment you completely control and where nothing can be stolen. Let's put it that way. But why you can't do that on an HPC system? There is indeed a lot of work on something like rootless Docker, but as far as I know, it's at least not far enough for us to trust it. So that is a little, that is a side note there. The last part of the question I don't understand. So is there a possibility to let users build Docker images but not run them? Okay, yeah, now I think I understand. So basically, you would want to build a Docker image on a system but not run it. That's your point, but I don't quite see why. Why would you want that? Maybe you can activate your microphone. That might
Yeah.
be easier than to put it in.
Yeah, our PhD students, they want to use Docker, and we also have OGPU servers, and the same reasons as you have on HPC, we don't let them work with Docker on the system. Similarity but they more and more ask for developing Docker, building Docker images. But then, of course, I don't want them to let them run on the system. So I want to know, is it
Yeah.
possible to build a Docker? Because yeah, we have the NVIDIA cards, everything that they don't have on
Yeah.
their machines. And
I would really have to think about that because maybe it's possible, but this is something that you're KU Leuven, if memory serves correct.
sorry, can you repeat your question?
You are KU Leuven staff.
Yeah.
If,
Yeah.
yeah. Okay. It might be better to take that up with ICTS and ask it.
Okay.
Because the people at ICTF have a lot of experience with Docker, but running services, and they know it quite well. So it might be that they have an idea how to do that.
Okay. Yeah. Thank you very much.
Yeah, because I'd have to try and figure it out, and yeah, I'm not really into that. So yeah,
Okay.
but
Well,
I see the point. Yeah.
yeah, that was my question there. Thank you very much.
Yeah. Okay. Then question from Elisa. Maybe a little later. Yeah. Okay. GUI applications. Yeah. GUI applications are not an issue. The only thing, of course, which you would need is on the host where you are running the container, you would need a working X server. That's pretty obvious. But apart from that, it works. So for instance, this Grace thing that I can likely show you. Where is that thing? Okay, so let's build that container. Fake root, grace.sif, and whether this will still work is actually a good question, because that has been quite a while since this was in use, so that might actually not work anymore. Okay, let's give it some time, and let me continue, because this seems to be... It's also based on a very old Ubuntu, so that might not work. Okay, so that about multi-stage builds. So what you can do is manually modify images, and you can do a mount of an image. You can make that writable, and then you have your image as a directory tree on your host system, and you can just go in, change things, add things, remove things, and so on. Should you do that? I'm not really very keen on that, because it is not an automatic part of your final setup. So if you have to go in manually and change things, then you don't have reproducibility. So I would say don't do that. Okay. So what can be useful is to inspect an image, to look at it without the writable. So just to have a look what's in there. That can be quite useful. Okay. It's also possible to do remote builds. So basically, that would require an account at Scilabs, and you can simply build using a web browser. So you, of course, need a singularity definition file, and then you can actually run those images from the command line as well. So you can also immediately do that from the command line, with -- remote, and then you get your image locally, but the build is in fact done at Scilab servers. Whether this still works with Aptainer would be interesting. I'm not so sure that that's going to work. You also need a token, of course. As you can see, you would really need to have a Scilab's token. Do I still have one? Very good question. No, that seems to be a very empty directory. Do I still have a Singularity directory? Yes. Okay, so I don't have a local token here, so I can't demo that anyway. But whether that is still supported in Aptainer is a very good question, given the rift between Aptainer and Sybase Singularity. Anyway, of course, the nice thing is if you can do a remote build, you also don't need sudo. But then again, okay, my image file meanwhile seems to have been created. So let's run that. So that's Aptainer exec grace sif, and then bin xgrace if memory serves. Not this time. Okay, let me just go in with a bash shell. Okay, and let's do a which xgrace. I don't have an xgrace. Which grace? I do have a grace. Okay, how do I get the X version of that? I thought that was xgrace, but because this is going to give me, yeah, that's going to give me the command line. So can I get Okay, it's too long ago, but yeah, it worked because I've actually done that. But I'm not really sure that this version actually does the build. Okay, let me get out of the container. Let's have a quick look at the recipe. That was Xenio Grace. Okay, yeah. This is indeed only going to do the non-X version. Ah, that's a pity. That I don't have the thing I actually deployed, but okay, doesn't matter. So yeah, it will work. XM Grace. Okay, maybe. Let's try. Ah, cool. Okay, yeah, thanks, Dominic. So yeah, here it is. So as you can see, it works nicely and without any hassle. But of course, I am on a host that has an X server. So remember that that's of course a requirement. If you're on a Linux system, that's automatic. If you're on a Windows system, it depends a little on what you're using. But WSL is not a problem. It will work out of the box. So great. Okay, so that was for this particular question. So yeah, it works, no problem. All right. And actually, that is also a very good use case because, for instance, if you need certain plugins for applications, and I'm thinking, for instance, of ParaView in combination with OpenFlow, then that sometimes requires some very bizarre setups. And that might also be something that's easier to do in a container rather than on bare OS systems. Okay, so there are quite a number of options to build your stuff from. You can also use a local container or a local archive as sources to build, and you have several things you can build to, etc., etc. But let's not go there. Okay, now for the kind of Apple presentation kind of thing. Oh yeah, and yet another thing. So actually, I don't often write Singularity recipes. In fact, I almost never do this. Why? Because there is a very nice tool which is called HPC CM. So HPC Container Maker. And that's a tool which is developed by NVIDIA because obviously they love containers because their software is easier to distribute that way for people to experiment with. Because yeah, setting up GPUs and correctly and so on is not always that easy. So that's one thing. And the other thing is that, of course, they also know that part of their important market is HPC. At least they were convinced of that. They're again convinced of it, but it took a little AMD to get us back fully on the radar. So they are faced with a similar problem, and they developed a very nice tool for that. So it's an open source project. It's very nice. And the point is that you write a Python script which defines your container. Let me just show you, because that's the easiest way to deal with that. And let me use the opportunity to also show something else. And that actually, yeah, I didn't deal with the second question. Sorry. Yeah, so the layer thing. So with development, you mean the development of a container. And yes, indeed, that is a little more convenient with Docker because indeed you have these layers. And the layer thing in Singularity, or in Aptainer, I should say, is not that well developed. So of course, one option is that people indeed just develop using Docker and then turn it into a Singularity container. But yeah, that is kind of obvious and doesn't answer your actual question. But anyway, so let's have a look at, for instance, development base. And as you can see, it's a Python thing. So I don't need to import anything, whatever, but this is all Python syntax. So basically, this is just some documentation about this particular script. Okay, I do import Padlib because it's a little more convenient than for certain operations. And then I start defining my image. And as you can see, there are a few things predefined, like for instance, stage 0. So that is the first stage of my build. And I can just specify the base image. And in this case, it would be an Ubuntu 21.10. Okay. Then I would install an editor and a number of tools. So I do that by adding to the stage 0 an apt-get for a number of OS packages. So I want Vim, I want less, I want ACK, I want Tmux, and so on. So basically the typical tools which I use when I'm developing software. Of course, I also need some archiving stuff. So I want tar, I want gzip, bzip2, wget, CA certificates. Don't forget CA certificates, by the way, or you will regret it. Then I also want to add pip. I'm just going to install it in the base image. I want tools like Git. I want an OpenSSH client. I want some specific build tools. So the build essentials. Yeah, I'm on Ubuntu. I want make. I want package config, etc., etc. And I want my compilers. And notice I can just do stage 0 plus equals GNU, and I get all the GNU compilers. So that's GCC, G++, G Fortran, etc., and all the development libraries which are required for them. Then I can even install OpenMPI if I want. I can either do it with the OpenMPI primitive, specifying some options. For instance, I can do that with support for InfiniBand, with support for CUDA, etc., and I can also specify the version if I want. So basically, that would ensure that OpenMPI, in fact, gets compiled during the installation of this image, which is, in fact, why it's commented out here, because I would only do that on an HPC system. Note that this is potentially very dangerous. So this is not necessarily a very good idea. So in this case, an alternative is to install using opt, and that is certainly a bad idea unless you're running this container only locally. Everything has been commented out because I don't need MPI in this particular container. Okay, then I also want some debugging tools, GDB, Valgrind, strace, etc. Hyperfine, okay, and just comment it out because this is not an image I usually build. This is intended as a base for a specific project. So if I want to copy in some files or whatever, I can do it here. So you recognize all the steps which we had in the Singularity recipe. So the apt-get would be similar to a post section. The base image would be similar to bootstrap from stage. So this is very similar, only the stages are not named here, they're numbered. And you have special primitives, for instance, for CMake here, or for OpenMPI, or for GNU compilers, and so on. So why do I do all this? Well, basically, because it allows me to, in a very transparent way, have a development environment which I can share with others, and which is reproducible, and which allows me not to pollute my operating system install with various libraries that I only care about in specific projects. So I have builds of this container. I'm not going to do it because this takes forever, but I have builds of this container. So container exec, and that is in mount C container, I think. No. What do I have here? Would that be an ops? No. Where did I leave them? Because I think I've been smart enough to do it differently on my laptop and on my unless they're just in my bin directory. That's also possible. I think so. So let's have a look at my bin directory, and let's look for files. Yeah, so yeah, I still have them here in my home directory apparently, which is different on my laptop where I have them in a system level directory. So for instance, if I run a different example, this is for one API. Okay, let's not do that. Let me run this one. Okay, so container exec. All right, and I want just a shell. Okay, so this is my container, and as you can see, even my prompt didn't change. well, yes, it changed because I made it change, because otherwise it's way too confusing. But now I'm in my container. But notice that actually my home directory is available in this container. See, this is my home directory on the WSL instance, which plays host. So basically, this is very convenient. And also the file system below your home directory is also completely available. So for instance, I could move to, now I have to be a little bit careful which example I give. Yeah, let me go to my home directory first. And then, for instance, I could go into Demo Magic here. Okay, so this is available. It was not the directory I started the container in, but my home directory is auto-mounted. And now, of course, I have my GCC here. And the GCC in this case is 11.2. Okay, so this is a version which is likely different from the one I have on my host operating system. So the nice thing about doing development, and now I'm talking about software development, not container development, using Apptainer, is that in fact it's totally transparent. And I can go to some directory. Let me go to my temp directory. I can create, or I probably have some stupid, test.c, for instance. So I can do gcc test.c. Okay. The ownership of my test, of my a.out is in fact just me. So I'm running in the container as the user. I'm actually on the host system. So this is completely transparent. I can hardly see the distinction between being in the container and being on my host system. But the entire software stack that I'm using in the container is indeed confined in the container. So if I go out of my container and I check the GCC version, and then you see that in fact it is an 11.4. So this is nice because if I want to experiment with, for instance, a different compiler version, then I can just create a development image, specify the specific version I want, a beta version, for instance, of the compiler, try things out from within the container, and I don't have to pollute my operating system with things I might regret later. Similar for all kinds of libraries. It might be that for specific projects I want specific libraries, but I really don't care about them outside of that project. So everything in that way is contained within a container, within an image. And in fact, I use this in production. For instance, here you will see a recipe that contains all the software which I need for this particular project. And that is in fact based on this image. Okay, back to HPCCM, because that was what it was all about. Okay, so I've got my recipe in Python. So why would I care? Because I know about Docker, I know about Singularity, so why would I care? Well, basically the nice thing is that this Python specification can be compiled down to a Singularity recipe. So HPCCM, you can install that with pip if you want. Then I can specify the format, and that is Singularity, and the recipe, and that would be my Python file. And as you can see, it writes, it doesn't, what's going on, where's packages? Yeah, okay. This was indeed 8th edition, and it's not in the image which is deployed. So apparently I made a typo. Okay, so I think this is better. Let's see. Yeah, and basically I get a Singularity image that does this installation for me. Okay, yeah, but I can change the format to Docker, and now I get a Docker file. So basically this is nice because with a single specification, I can either get a Docker file or I can get a Singularity file or an Obtainer specification. So that's rather nice. And I get something extra. I can even get a bash script that would install the whole thing just in an existing operating system. This is, as far as I know, you can only generate for Debian-based systems, not for things like CentOS or Rocky or something like that. Okay, so this is really, really cool, and this of course helps a lot if you have what I would term a mixed workflow, where you in some circumstances need a Singularity recipe, and in other circumstances just need a Docker file. Easy, just write a Python specification, make HPCCM generate either a Docker file or a Singularity or Obtainer recipe. Very easy. So I'm a big fan of HPCCM and use it most of the time. Okay, so there is a caveat here, most of the time. It doesn't play well with multi-stage Singularity recipes. So it's entirely possible to write a specification for HPCCM in multiple stages. That works. For Docker, it will generate a correct Docker file. For Obtainer, it will generate something you need to work on. And that is a little inconvenient. So that's why if I want a multi-stage build, I'm not going to use HPCCM. Because yeah, okay, it works for Docker, but not for Singularity. I've tried it yesterday with the most recent version, and no, it is not able to copy from one stage to the other. Yeah, and that's a crucial feature. If I don't have that, I don't really care anymore. So yeah. So I hope that in a future version that will be fixed, but at the moment, that is not happening. Okay. So this is quite convenient. So this would be an example, but I've shown you in real time. And then you can compile down and of course, or translate to, and then you redirect the output to some file. Okay, that's easy. Right, using images, you've seen me use images already quite a bit. So if you have a run script specification somewhere in your Singularity or Obtainer recipe, you can just use Singularity run, and then that command is going to be executed. Typically, I find it more convenient to use exec, but okay. So some directories will be bound. That means made available within your container automatically. One of the things is your home directory, also temp, var temp, and these kind of directories. So that's convenient. Exec is your friend if you want to use a specific command. So for instance, there is also grace bat, which allows you to run a grace script in order to produce a certain plot. And then you need to specify data and you need to specify a definition file for your plot. So that's also possible. And as you've seen, if I want to use an Obtainer image interactively, I typically also do this exec, but then with bin bash, which gives me a bash file. I could add that to the as a run script section in my recipe, but typically I don't do that. Okay. XM Grace. Okay. Should know my own slides. All right. So can you integrate this in a workflow? So specifically in a job script? Yes, of course you can. Yeah, okay, please translate this to Slurm. I'll have to do it at some point, but basically it doesn't really matter. The heart of the matter, of course, is that you can just execute obtainer exec like you would do on the command line, and it doesn't really make a difference. Remember that if you do that concurrently many times, so if you have a job array or you have a worker or a tools thing running, then of course that is a bit of a load on the file system, and you might want to actually try and minimize the size of your image. However, in fact, this is a blessing, because one of the things that really hammers the file system is this situation where you are running embarrassingly parallel workloads, and you're doing that with R or with Python. Because they will, when you execute a script, they will start loading 500 million libraries with 500 billion dependencies, and those are separate files. So that's a lot of metadata I/O and a lot of I/O in general, which is hammering your shared file system. And so basically, if you start a job array either through a tools or a worker job with I don't know how many work items, that is a big burden on the file system. Interesting. So if you would pack the whole lot into a container, that means that rather than 500 million file accesses, you will have only one per run. A lot less demanding. And in fact, if you read the documentation of the Lumi cluster, that's what they actually very strongly recommend, because that's the, well, okay, I won't say the only way which they can allow you to do R or Python at scale on such systems, but it's definitely good practice to do this. There are caveats. We come back to that. Okay. Essentially, singularity images can be used in any workflow. You can combine several singularity images. That's not a problem. Okay, you can also immediately run a shell. I typically prefer to do singularity exec or obtainer exec image and then bin bash, because then I am pretty sure which shell I get, and it's also an interactive shell, so it will be initialized properly, etc., etc. Okay, so that's the reason why I don't do that. So one of the things which you have to keep in mind is that your home directory is auto-mounted. So that means that if bash starts up in the container, it will actually use your .bashrc to initialize your .bashrc, which lives in your home directory. So that means that you can have errors because some things which are in your host .bashrc don't make sense within a container. So that's something that you need to keep in mind. And typically, I guard against that by making sure that things are not loaded if they don't exist. So for instance, okay, this is all crap. Let's see where it gets more interesting. That's not interesting. That's not interesting. Lots of stuff is not interesting. Okay, so for instance, one of the things that I do is in my prompt, I want to see the GitHub branch I'm on in a given repository. And there is a nice script to do that. It's git prom, blah, blah, blah. You source it from your bash RC, it works automatically, and so on. But of course, if you just put source, etc., for something, then that might not exist within the container. In this case, it's not a problem because it's also in my home directory, so everything will work. But that's not true in general. So I typically guard that by testing whether that script in fact exists and only then sourcing it. So this might be the kind of precaution which you might want to take. Okay, so I typically do that for everything. Of course, things like this, adding stuff to the path, will make little sense within the container because it's very unlikely that there is a user local Go bin directory. But okay, that is not a problem in the sense that, okay, if that directory doesn't exist, nothing is going to happen to it, so it doesn't matter. But you have to be a little careful. One of the things you have to be very careful about, let me just show you. We had our Conda container, and I think I built it. Yeah. So let's actually execute it. Let's run it. And I'm going to ask for a shell. All right. Which Python? Looks good. No, it doesn't look good. What is happening? Well, basically, given that my path is being set in my bash RC and that this directory is added to my path, so this is the equivalent of Miniconda tree. Basically, it means that if I'm not careful, I'm actually going to use the Python on my host system, and that will in fact work. It's not a problem. So if I do a version, it works. But this is not the Python I intend to use. Remember, I had this Conda environment within my container, and that contained NumPy. So if I run this Python, and I do import NumPy SNP, which I expect to work, doesn't exist. No, of course it doesn't exist because this is not the Python in the container, it's the Python on the host. Okay, let's get out of that. Let's run the correct Python, which is here, and that's of course in env bin Python. So you see, this is a higher version. It's 3.12 rather than the 3.10.8, which is on my host system. And if I run this guy, of course, I can happily do import numpy snp and np, I don't know, linspace 0, 1, 11, and I get what I want. So this is a little tricky with Singularity. If you have something like R, if you have something like Python, and you do stuff with your path in your .bash RC, you have to be very careful because you might not be using the versions of stuff which you expect to use. For instance, for R, in your home directory, there might be a .r something something environment, I think, which contains some useful stuff. No, that was not the plan. I don't seem to have any R-related things here, which is good because I don't use R here. I don't even have R installed. But for instance, as you can see, R environment, and that, okay, I'm in my container, I don't have less here. So let me just cut. I'll go out of my container in a minute. So basically that sets the time zone and so on. But it can also do things like set directories where packages are installed. So be careful, because again, you could start using packages which are on the host, which might not be what you want. So be careful there with configuration files. Let me escape the container. Okay. So that's a little bit about that. Okay. So directory bindings. So the current working directory is always bound, and also your home directory. So basically that means if you're on an HPC system, your home directory is on a certain file system, your data directory is on a different file system. So if you start Apptainer on VSC data, it will actually make the working directory at that point, but nothing above. So that is something to keep in mind. So if you want to do additional bindings, for instance, of VSC Scratch or other directories on VSC data, you can use the -b flag, and that takes host path and image mounting point. So for instance, you can do a directory data mounted, which is in your home directory, and you might want to mount that to the image mount directory data. You can do that. You can also use a single argument, and then that entire directory is mounted with the same path as it is on the host. So that uses overlays. Let me perhaps show you on the HPC system. Let me quickly SEP a container. Let's use yeah, it shouldn't take. I'm going to use the multi-stage thing because that's a very, very small one. So if I do the multi.sif, and I want that to go to Genius, I want it to be in my home directory. So that should work. Yep. Okay, let's go to Genius. I'm in my home directory, so let's Apptainer exec multi, and I want bin sh. Okay. So no, that was not what I wanted to show you. So if I want to ls ops, data version 301 VSC 301, okay. Then yeah, okay, can't do that. All right, let's exit this. Now let's bind the data directory. So -b $VSC data. Okay. Now let me re-execute that ls thing. Data Leuven, as you can see, tab completion works. So, and I have access to my data directory. So really, really convenient. If I have a job script, or if I have software that relies hard-coded on absolute paths, okay, it will work if you do this kind of bind mount. So these are overlays. So this is really convenient that you can actually do that. That's transparently supported by Singularity, well, by Apptainer. Okay, if you use a specific mount point, then it must exist unless overlays work, but overlays do work anywhere that I know. And you can have multiple B flags, so you can mount as many directories as you wish, no problem. Okay, another thing which is quite convenient is the --nv flag. So let me put that in the chat. So essentially, if you want to use a container that contains CUDA stuff, then that's actually quite convenient. You just specify NV. Obtainer will do 1 million extra binds. Make sure that the drivers are exposed in your container, and that you can just run your NVIDIA compilers, for instance, or whatever. So, for instance, I do have an environment. Okay, let's try to spell this correctly. An environment here. No, I don't. Okay, I'm on the cluster. Okay, no, I don't have that there. So for instance, I do have a CUDA development environment. I also have an. No, that's it. I should have an HPC environment. It's possible I don't have it on this computer and only on my laptop. But basically, it allows me to run any CUDA HPC compiler just simply from a container without having to install the whole thing. Okay, so multi-threaded applications, it works. There is extremely little overhead. So this would be installing your own application. Let's not go through this. This is almost pretty straightforward. One of the things which are kind of obvious, you don't need the same compiler version in the image as you have on the host. That is independent of one another, so that can be quite convenient. If you need a more recent compiler or a very old compiler, okay, just define a container for that. So MPI. MPI is a lot more interesting because, of course, on HPC systems, a lot of care is taken to configure MPI optimally for the hardware which supports the high-speed network, be it Slingshot, be it InfiniBand, be it Omnipath, whatever. So that takes HPC support staff quite a while in order to get the configuration optimal for various open MPI implementations, such as Intel MPI, such as OpenMPI. So you can use MPI for running applications in containers, but then the advice is that you use the exact same version of MPI for your build as you plan to use on the system. That is quite important. And of course, you can use the Mellanox drivers and so on. This is pretty old, so don't rely on this. Check which Mellanox drivers are present on the cluster you're using and make sure that you get those into your image. Okay. So basically, you install your software and then you can run it just with MPI run. So this is an example for OpenMPI. You can just use MPI run. This is all on the host, and the container will only run the application. So basically, it will rely on the OpenMPI installation of the host in order to run the processes. So test management is done by the host. The actual run times for MPI are the ones which are in the container, but those communicate with the MPI daemons or process managers on the host. And that way you get very good performance. There is a little bit of overhead, but it is fairly limited. It's of the order of 5 to 10%, which is something that is very often negligible on HPC systems, since just due to varying load and so on, that's something you see anyway. Okay, so Services, so you can run images as services as well. For instance, if you want a database, then you can create a Singularity image that contains that database, and you can run it as a service, also with web services and so on. So that is quite easy to do, but of course you need to set up processes and you need to clean them up properly. So the workflow is typically that you start a service, you do client interaction, and then you stop the service. That's the typical thing to do. And this you can do using Aptainer instances. So this would be a server definition. So basically, this is an Alpino server. That's a natural language server. So you define what happens when it starts. So in this case, it does lots of stuff, and what it should do when it stops. In this case, in the case of a Alpino server, that's not relevant because it's not persistent. It has no persistent data provided by the clients. If this is a database server, then of course you would have a database start here, and in the stop you would have a database stop, which makes sure that all the data that has been added, modified as transactions during the runtime of the database is properly stored into its persistent data structures. Okay, and then you can simply start the service, you can stop the service, that's to test, and then the recipe will actually contain a start script for Alpino. And that is just what should happen when it starts, and you have a corresponding stop script as well. In this case, of course, for Alpino, you don't need to bother with the stop script, but you should specify that when you have a proper service. So that it can be very convenient. To run an instance, you just do Aptainer instance start, you do the necessary bindings, you specify the CIF, and you specify a name for that particular instance. So Alpino 0.1 is one instance. You can have multiple if you want. So that's basically how that works. Then you can interact with the instance, and you can do a Singularity or Aptainer instance list that gives you all the running instances, and you can stop it using instance.stop. So quite straightforward, very easy. You can have as many databases running, for instance, as you want. You can have a database running and the web server running, have them communicate with one another, etc. So this would be sort of the equivalent of Docker Compose, sort of the equivalent of Kubernetes, not really, but okay. Docker Compose more or less. Okay. Very important, performance and best practices. So there is an overhead, of course. So it takes half a second in order to start up an image. Okay, does that matter? Yes, if the run of your Singularity image takes a second, then you suddenly have a 50% overhead. However, if your Singularity image runs for an hour, you don't care about that half second. So don't use Singularity images for things that have extremely short runtimes, because then you're being very inefficient. You spend, well, a lot of time just starting up images. Okay, if you have short runtimes, ensure that everything goes in the image itself, that your workflow with many short runs is in the image itself, rather than in the image, out of the image, into the image, out of the image, etc. So for a serial code, the overhead is really negligible. As you can see, it's less than 1%, so that is unnoticeable. And it is, as far as I can see, independent of the number of threads. For MPI, there is a bit more overhead. So it would be 7% for 16 processes, 24% for 64 processes. These are fairly old numbers. So basically, as you can see, it's also application dependent. So if you have a lot of interaction, a lot of I/O overhead anyway, then you will see it more than with less I/O overhead. So in singular value decomposition, distributed over multiple nodes, is computationally, of course, heavy, but also with respect to communication, pretty heavy. While it's much easier for matrix-matrix multiplication distributed over multiple nodes, then you have much less communication and hence much less overhead. These numbers are fairly old. I should at some point redo this with more recent version of, with the most recent version of Obtainer and check these results, because this really dates down to 2016, I think. So this is really old. But just to make you aware that if you don't need containers for MPI, I would suggest not to use them, because there will be overhead, that's for sure. Okay. On the other hand, there is also overhead for some reason for a singular value decomposition, which is not distributed, so which does not use MPI. The reason for that is likely memory interaction. So yeah, it depends. You need to benchmark. That's the bottom line here. So one of the pitfalls is that you do not use optimized libraries and applications in your image. Okay, so always try to build your images on the target hardware. It's the same as for applications, so try to do it on the target hardware. So for instance, on my laptop, I have a Skylake CPU, so I can build images there, transfer them to the cluster, and they will run at near optimal performance. On the other hand, on my desktop, I have an AMD CPU, which does not support the same vector instruction set as Intel CPUs, so I have to be a bit careful because factorization will be suboptimal when I generate an image on my desktop system. So that's something to take into account. So if you can get away with fake root, and as you've seen, everything I tried with fake root actually worked, then build your Singularity image on the hardware you intend to run it on. For instance, there would be no way for me to use Ice Lake vector instructions. Okay, mostly it's Skylake, but there are some specific for Ice Lake, since I don't have an Ice Lake CPU except on the cluster. So that's something to keep in mind. So all compilations within your image in that case should be for Intel with Xhost or with mark for GCC compilers, so that you make sure that the target hardware is being targeted. Yeah. So this may lead to much larger performance impact. So that can be 10 to 40% or even more in bad cases. So that's something to really keep in mind. And of course, for libraries such as BLAS, etc., that is really critical, because if you use a BLAS library in your image which is suboptimal, then of course you're going to really, really miss out. So that's very important for BLAS and anything that depends on it, like LAPACK, PET-C, etc., etc. Nowadays, you have to be very careful with Conda as well, because in the past it would default to the Intel MKL for that kind of libraries. I noticed recently that it doesn't anymore. So that is quite important for the Python people who use Conda and rely on the fact that they get MKL. No, you don't get MKL anymore by default. So keep that in mind and use the Intel Python distribution as your base image, as your base Conda environment, and build on top of that. That will give you really excellent, superb performance. Okay, and then Bootstrap best practices. So what you typically do, and what we do on the cluster, is using modules in order, because we don't want to install software in the default locations. In images, do that. Just install into bin, install into lib, it doesn't matter. It can't conflict with anything because your image is purpose-built. So just put it anywhere it would normally be done by default. Don't bother about separate locations. Define environment variables in the image. So make sure that you have proper path name, proper paths, etc., etc. Files should be owned just by the system account. Don't bother with permissions. It doesn't make sense. There is only a single user, which is you, in that container, so you have access to anything anyway. So it doesn't make sense to set permissions, whatever. Don't bother. There is no sense in that. This is all for Obtainer, of course. Do not ever mess with etc password, etc groups, etc shadow, etc., etc. Don't touch those. Bad idea, because then you will mess up your compiler, your container royally, and it won't run, or certainly not as expected. If you want to do user management, and there is a nice use case for that, for instance, very specific training material, if you want to use containers in order to train people, there is an example of that somewhere. Let me see. I think I have that in development note. So let's have a brief look at that recipe. Do I do user management here? No. That is a pity. That is a pity. Because I spent a lot of time on that, and apparently it's not in the repository. Oh, that is so bad. Okay, I have to find that again, and because I really spent a lot of time on this. So, okay, yeah, whatever. So it can be done, and I did that for training where I created a number of users in an image, deployed that image on an Amazon cloud instance, and let people SSH into that image in order to do a training. So you can do it, but it requires a little fiddling. One thing which I find very important is never modify an image by hand. That defeats the purpose of reproducibility. So always do that via recipe files. So yeah, that's very important. Okay, so I'm at the end of the session and only 3 minutes over time. So Singularity definitely has, well, Obtainer definitely has a lot of advantages. I've talked about it at length, so I'm not going to reiterate that. But I would like to point out the bottom line. So for those of you who have been at the user day, one of the things I said during that talk was you are using a tool. And a tool is just a tool. So basically, if you don't know how to use it, you are going to, hammer yourself on the foot, basically shoot yourself in the foot royally. So you really have to know what you're doing with containers, and that's what this training is for, just as you need to know what you're doing with any tool. So, of course, it can never be an excuse to run crappy or suboptimal software. That's only allowed, let's say, only something you should do when you really have no other choice. So don't use containers unless you have to. And have to can have many, many arguments why you would want to do that. And I've given you a few. But still, in your containers, don't use suboptimal software if you have a choice. Build your containers on the target system. Make sure that things get compiled with the right flags, like xhost or mark, whatever, to target the hardware which you're going to run on. Don't use suboptimal libraries. Don't use libblas. It's a reference application with respect to performance. It's crap. Make sure that you either have OpenBLAS or MKL, things like that. So that's really, really important to take all these things into account. There are a few references. User guide is definitely useful. To GitHub repositories there, there's a link to HPCCM, a Wired article, okay, why use Singularity? So it's fairly old. That will not be very interesting. Okay, so on certain HPC systems, you can in fact use Podman rather than Docker. So you can use containers there without sudo. It can use rootless containers, so without a daemon, and the commands are the same as with Docker. So if you're a Docker lover, you can consider using Podman on those systems where it's supported. Last time I tried, it was installed on HPC infrastructure in Leuven, but didn't work. So, well, didn't work without root privileges. So kind of useless for users, but it can be configured in such a way that it can be used. So why am I talking about Aptainer if you could use Podman anyway, which is a drop-in for Docker? Because there are definite advantages to using Aptainer. For instance, everything is a single file, so you can run the same thing later on, which is also possible with Docker if you're very careful and specify each and every version. Okay, so I prefer Aptainer images to Docker, Podman, whatever, for that reason, and also because it's much easier to just launch an Aptainer image and use it for development. Again, you can do that with Podman, sort of, with Docker, somewhat, sort of, but you need to configure it correctly. You need to give a million command line options in order to get it to do what you want, while it's trivial with Aptainer. So that's why I actually prefer Aptainer to Podman, Docker, whatever. Okay. That is not particularly interesting, so we skip that, and we are actually at the end of the presentation. Are there any questions left? No more questions from your part. Okay. Nope. All right. So in that case, I'd say nice seeing you here. I hope this was somewhat useful, and yeah, I wish you a pleasant remainder of the day. And maybe see you in some other training in the future.